So let's talk about radical functions in terms of what they look like. So remember a function, f of x. What I'm going to do is I'm going to write this as the square root of x. And what this is called is, this is my parent graph, or my parent function. And what that means is that's the most basic square root function, and then everything else can happen to it. So when we have this square root, we have to remember that what is underneath the radical is called the radicand. And that means this entire expression must be greater than or equal to 0. So when you are graphing radicals, or even just talking about their domains, the domain is all the values that you're allowed to put underneath this radical. So it's okay to be taking the square root of 0, but it's not okay to have a negative. So oftentimes you will see an additional inequality symbol to denote what values you are allowed to use. Right? And so just a quick little idea of what this looks like. Right? All right, so if you think about how radicals work and the fact that you want perfect squares, right, I'm going to use, starting off here at 0, I'm just going to do a couple little values. Not a whole lot. But if I think about making an in-out table, what happens with the value of x, and then what happens with the value of y. Right? Now you always start off with the first point in your domain. This is going to end up being called my initial point. We're going to talk more about that shortly. But your initial point is always starting off with what is the smallest y value, or sorry, smallest x value I can use in this radical. So since I'm not allowed to use negatives, I have to start with 0. So if I plug 0 into the square root, I get the square root of 0 is 0. Okay, and then I'm going to go with my next number, and again the square root of 1 is 1. But now once I start using other values like 2, 3, I'm going to be getting that it's the square root of 2, which is some decimal that I don't know what it is. So when we're trying to graph, we tend to not use values, if we can help it, that are going to give me a decimal. So what I'm going to do is I'm going to start thinking about picking values that are perfect squares. So I'm going to jump over 2, and I'm going to jump over 3, and I'm going to say, well, let's go straight to 4. Because the square root of 4, right, is now 2. And so I'm going to want to use this initial point and then some other perfect square inputs. So what your function looks like is it starts here at 0, 0, and it doesn't have an arrow. It starts specifically there, and then goes to 1, 1, and then goes to 4, 2. And it would keep going in this manner, like this. Now the right-hand side does have an arrow because I can continue to put x values in that are positive and keep my graph going that way. So that's our generic parent graph. Right? So when we're trying to look at other graphs and how we're going to manipulate that, right, that's how we get this kind of more generic or general function, which we have as a times the square root of x minus h plus k. And so what's going to happen is, again, as we've seen in other types of graphs and transformations, this a value is going to either stretch this graph up or down, flip it around, right? But I have to think about this x minus h because that's the radicand. And so when we are looking at for our domain, right, our domain is going to be any values where x minus h, or whatever the expression is going to be greater than or equal to 0. And you're going to need to actually solve that and do some work to find out the specific value. The other thing that we're going to need to see is, just since we started talking about initial point, right, your initial point when we start graphing these later is going to have the x value as whatever happened when we solved x minus h to be equal to 0, and then my k value. So we're going to have to do a little bit of work to figure out and say where is this going to start? And then k is going to move us up and down. All right, so it'll say it's going to move left or right based off of x minus h, and then up or down based off of k. So let's look at how we're going to find the domain of a few of these functions. I'm going to get some more space here. So our goal right now is just to find the domain. All right. So let's look at an example. And I'm going to look at f of x is going to be equal to 45 root 2x plus 1 and then plus 19. Now I'm not going to worry about graphing this. I really don't care what the graph looks like right now. All right? But I want to be able to look at the domain, and I'm going to look at the domain in two different ways. So the first part is based off of this radicand. I need to set up my inequality to say when is the radicand greater than or equal to 0, and now I'm going to solve. All right. So when I move my 1 to the other side, it becomes negative. And when I divide by 2, I get that x has to be greater than or equal to negative 1/2. And so I'm going to look at that graphically for a minute. All right. So here is negative 1/2. And I want to think about my number line. And on the left-hand side goes towards negative infinity. And the right-hand side always goes towards positive infinity. So negative numbers to positive numbers from left to right. All right. Now this greater than or equal to symbol means all the values for x that are greater are going to be to the right. All right. So I get to use negative 1/2 because of the equal to part. And I want all the values going to the right. And so when you're talking about your domain can be written in multiple ways. One is like this, right? And this is called inequality notation. Right? Because your solution or the values of the domain, the values you get to use, are used with an inequality symbol. The other part is what we call interval notation. And so interval notation says that if I get to include this value, I'm going to start with a bracket to show that that value is included. I have to use the value that I get to start with, and then the direction of the arrow is going to say move towards infinity, and I don't know where infinity stops, so I need to use a parenthesis. And this is what we call interval notation, because it gives us the interval of all of my solutions. Right. So inequality notation has an inequality symbol, and interval notation does not. Right. There's a third way that we could talk about this, and that's also in terms of what we call set builder notation. All right, and so set builder notation is using these little brackets. This is how we denote a set. And it says all the values for x, right, such that, and you use your inequality. X has to be greater than or equal to negative 1/2. And so with your set builder notation, it uses the inequality notation, but it uses these little set notes. And this little extra line says all the values for the variable I'm using such that this is a true statement. All right? So these are three different types of notations you can use to talk about your domain. And we're going to talk about all three of those multiple times.